new chapter 15. And in this chapter, we will be learning, about organometallic compound. So the first, we need to, learn what's definition. What is organometallic compound? So as the name suggests, the compound must have both metal and organic component, but that's not sufficient, to define organometallic compound. Really, definition is really you have to check whether compound whether has a carbon metal bond. So basically, organometallic compound, refer to those compounds that at least has one carbon metal bond. So for example, in organic one, we have seen this compound, conjugate base of acetylene. We call sodium acetylide. This guy actually is an organometallic compound because it has a sodium carbon bond. So it's, sodium is metal. So this compound is organometallic compound. But on the other hand, the sodium methoxide is not a organometallic compound because of in the sodium methoxide, you only have a metal oxygen bond. You don't have metal carbon bond. So sodium methoxide is not, the organometallic compound, but this one is. And there's a huge diversity of metals and the nucleophilic nature of the carbon in those, the organometallic compounds make them, very interesting, to organic chemists. So that's, the reason why organometallic compounds are interesting. But in this chapter, we're gonna learn a relatively, simplified version of organometallic compound. We're mainly learning organolithium, organomagnesium, and organocopper. Only those three compounds. Okay? Three kind of organometallic compounds. Before moving on to, see the reactions, of the organometallic compound. First, let's just briefly look at nomenclature of organometallic compound. In general, if we have organometallic compound, we always consider the metal is a parent, and the organic portion is named as substituent of metal. So like in this compound, the metal lithium is a parent, and the rest of the organic portion is considered as substituent. So this one, if we consider substituent, we call the cyclopropyl group. And the lithium is a parent. And keep in mind there's no space between cyclopropyl, the name, and the lithium. So the cyclopropyl is the substituent. Okay, so this is substituent, okay? And the lithium is the parent, called cyclopropyl lithium. And the same thing, this guy, sodium is a parent. So this one is a parent, okay? And the rest of this one, when it is a substituent, we call it vinyl group. So we call vinyl sodium. And similarly, the last compound, magnesium, is a parent, okay? And it has two ethyl group connected, so we call it diethyl magnesium. And in some organometallic compound, you might have, in addition to carbon metal bond, you might also have halogen metal bond. And as we know, we generally consider halogen is the most electronegative group of elements. So we treat the metal halogen bond as if it were ionic. So look at this example, we treat, well, with my cursor, okay. This bond is ionic, so we name the halide part as a separate, anion, we call iodide, okay. And the rest of the compound, again, the metal is the parent, and the organic one is substituent. So this is the parent, okay, and the metal is substituent. So it's the name consists of two words called methyl magnesium iodide. And similar here, you have alumina chlorine bond, and again metal halogen bond. So we treat the halide part is anion, and the rest of them is a cation. So we call the rest of them alumina is a parent, and the two ethyl substituents connect to alumina, so called diethyl aluminum and space chloride. Now the carbon metal bond is quite different from the kind of the bond let's say carbon related covalent bonds we have seen so far. The most of the carbon centered covalent bonds, either the carbon is not polarized, or the carbon carries a partial positive charge. The best example we probably have seen is the one we learned in organic one, alkyl halide. In alkyl halide, the carbon halogen bond is the highly the pair of electrons is highly polarized to the halogen side. So that makes the carbon in alkyl halide electrophilic, and because of the carbon carries a partial positive charge. But in carbon metal bond, doesn't matter what kind of metal we have, most of cases, okay, the metal electron activity will be substantially lower than the carbon. So in this covalent bond, the pair of electrons is strongly polarized toward the carbon. So the carbon in the carbon metal bond carries substantial amount of negative charge. So that means the carbon in organometallic compound, basically the carbon that connect to metal, is what? Is a nucleophilic, okay, organometallic compound in vast majority of organometallic compounds, okay? Not all, because as we're gonna see later, the look at the electron activity table. In some cases, the metal, the electron activity is very similar to carbon, then probably is not nucleophilic. So these are the electrostatic potential map shows the electron distribution of three relevant compounds. One is methyl lithium, one is methyl copper, one is the methyl fluoride. As you can see in the methyl lithium, the carbon connect to metal, has a pretty intense red color, means negative charge on the carbon, okay? And on the methyl copper, the negative charge on carbon is substantially lower. If you look at the color, the copper is somewhat positive polarized, and the lithium is highly positive polarized. So as a result, this carbon is somewhat negative polarized. Okay, and in sharp contrast, if you look at methyl fluoride, the negative charge is very heavy on fluorine, and on the carbon, it has substantial amount of positive charge. So that's why in methyl fluoride, carbon is electrophilic, and in the methyl copper, carbon is weakly nucleophilic, and in methyl lithium, the carbon is highly nucleophilic. And someone, let me see, seems someone raised the hand. Alan, you raised hand. What's your question? What is your question? Well, how can non-metal be more electronegative? That the look at the electronegativity. Look at a periodic table. I think there's a one electron. We're gonna see later. We're gonna see quickly. The next slide, I believe. Okay, look at this electronegativity table. There's always non-metal. They are more electronegative than metal. That's a general trend. So if you look at any period from left to right, always the right side is more electronegative and left side is less electronegative. And you know that the right side generally is they are more likely to see non-metals, okay? And the left side you generally see metals, okay? This is the general trend of all elements, okay? But anyway, so what you can see if you look at all the metals, even the least electronegative metal, gold, okay, its electronegativity is still somewhat lower than carbon. So you can say if you carbon a gold bond, it's still somewhat, the polarized to the carbon. But in that case, if you have a carbon gold bond, it's it's highly covalent. That doesn't have much ionic character. Okay, but if you look at the carbon lithium bond, the electronegativity difference is huge, 1.5. So similarly carbon magnesium bond, okay, the electronegativity is 1.3. So these two kind of carbon metal bonds is the kind of carbon metal bonds we're gonna be seeing most frequently in this chapter. And basically the carbon lithium and the carbon magnesium, because of the large electronegativity difference, so we can consider in those two classes of organometallic compounds, the carbon can be considered behave more like anion, okay, and the metal we can consider its approximation, consider they behave like a cation, okay. And if we have a carbon copper bond, that's kind of different. Copper bond electronegativity difference only about 0.6. In that case, we consider it's quite more like a covalent bond, okay. But the carbon lithium and the carbon magnesium, we can approximately consider those bonds are ionic, where the carbon is negative charge and the lithium and the magnesium, they are positive charge. So just for just simplified approximation. So if you have methyl lithium, okay, you can consider approximate, okay, it's equal to CH3 minus plus lithium cation, okay, because of the carbon lithium bond is highly polar, so we can approximate it just for the sake of simplification, easy to think about, okay. We can consider methyl lithium just equivalent to the methyl anion plus lithium cation. And similarly, you have organomagnesium compound, say methyl magnesium chloride, right? We can consider equal to, okay, methyl anion plus magnesium cation plus chloride anion, okay? So those are approximation, okay? So they will help us to understand the reaction. And the copper is different because copper, organocopper compound, we consider they are covalent, okay? Anyway, so then let's then look at the preparation of organolithium and organomagnesium compounds, okay? So the organolithium and organomagnesium compounds, if you look at what I written here, both these kind of compounds can be considered as the anions of the organic portion, okay? So just for the sake of simplicity, whenever we consider reactivities of organolithium and organomagnesium compounds, we consider they are the same. I mean, to be exact, certainly there will be subtle difference among these two kind of organometallic compounds, but just it's sufficiently correct for us to consider at this point, consider organolithium and organomagnesium compounds. They are the same. All of them, they can be considered as the supplier of organic anion. Okay. Yes. So here, methyl in these two examples, okay, the organolithium and organomagnesium compound, we can consider they are equivalent to supplier of methyl anion. Then how do we prepare those organolithium or organomagnesium compounds? Okay, so the organomagnesium compounds, they also called a Grignard reagent. So the most common form of Grignard reagent is you have one organic portion, R, organic portion, magnesium, then X is a halide. Those are the general formula of Grignard reagent. So organic anion, magnesium, and halide ion. This is the general formula of Grignard reagent. Okay, so the preparation of organolithium and Grignard reagent, they are very, very similar. Both these kind of organometallic compounds start from organic halide. Means, see, I say organic halide means it's not limited to alkyl halide. It could be, the aromatic halide also work. Vinyl halide also work. The key part is a carbon halogen bond. So this is one of reagent, organohalide, but the other one is a highly oxidizable metal, either lithium or magnesium. They are very similar. Okay? So they basically take the organohalide, react with the lithium, and it requires 2 moles of lithium, and give you lithium plus lithium halide, and this could work with the alkyl halide, aromatic halide, and vinyl halide. And the typical reaction condition is mix the halide and the metal in a dry ether solvent, diethyl ether, okay, or THF. So let me just draw the structure of the two commonly used solvents. One is diethyl ether, one is THF. Okay, so if you look at both solvent structure, they are kind of very similar. So only difference is between these two is that if you connect the 2 carbons, okay, in the diethyl ether, connect these 2 carbons, you get a THF. So this is called tetrahydrofuran. Tetrahydrofuran, okay, and this name is derived from here, and I hope you recall what we learned in chapter 13. This is a 5-member ring. This is called furan, okay, and basically furan added 4 hydrogen, you get a tetrahydrofuran, okay, and and if you're gonna use it in organic chemistry, let's say in a test or something, you just can write a THF to represent this guy, okay, and this guy has a higher boiling point than THF. About this 60 something Celsius degree, this about 35 Celsius degree. So for this reason, THF is more commonly used, than diethyl ether. But anyway, the key part is you cannot using alcohol as a solvent, you cannot use water as a solvent, and this reaction has to be the extremely dry, and I will be explaining why that's the case very soon. Okay, so why we need this kind of solvent, because of this kind of ether solvent has the oxygen atom. Okay, so and this oxygen atom can form complex with metal. Okay, it can help dissolve those organometallic the compounds. Okay, and also this reaction must be completely, free of any acidic hydrogen, like alcohol, water. It cannot exist. Okay. And similarly, you also can, let the organohalide directly react with the metallic magnesium, and similarly solvent using either diethyl ether or the THF. And if you noticed, okay, in these two reactions have different conditions. In case of alkyl halide react with lithium, you don't need to heat. You actually keep the temperature low, okay, to avoid the reaction going too fast, out of control, okay. But in case of you use aromatic halide, you need to warm up a bit, okay, for the reaction to proceed smoothly, okay. And this is actually has something to do with the the reactivity of those halides, okay. So first, let's, if we want to look at what is the general mechanism of the organohalide react with metal. First, we want to look at how the type of halogen can affect the reactivity. Let's say if you have bunch of halides, so alkyl part we fix it, okay, and then we the only the halogen is different. All of them react with, let's say, magnesium, okay, in THF, same temperature, okay, and then we compare their reactivity. We will see that iodide is most reactive, and the fluoride is the least reactive. Okay. So what's the implication? What kind of inference you can make from this observation? So can anyone tell me what kind of inference you can make from this the first observation? Halide, iodide is most reactive, fluoride least reactive. What kind of inference we can make? So anyone? Yes, very good. Okay. That's exactly I want to hear. Okay, because if you look at carbon halogen, if you look at the halide reactivities, most important thing about the halogen halide is that all these four compounds, okay, has a carbon halogen bond. Okay, and as we know, carbon fluorine bond is strongest, carbon iodine bond is weakest. Okay, so if carbon halogen bond cleavage is involved in rate limiting step, you will observe this kind of order of halide reactivity. So this observation suggests that carbon halogen bond cleaved in the rate limiting step, okay, break in the rate limiting step, okay. Now, second one is alkyl halides are more reactive than aromatic and the vinyl halide, okay. So that means that, let's say, if you compare, these two halides, okay, these two chlorides, okay, you do the same, solvent. Say, the two chloride react with magnesium in the same solvent, you will see this halide will be more reactive than this chloride, will be substantially more reactive than this chloride. Okay, why? Again, the inference is you are breaking the carbon chlorine bond in the rate limiting step. I hope you, I repeat, emphasize, or many times already. If you look at the carbon X single bond, okay, that single bond strength depends on the hybridization state of carbon. So in both these two carbon chlorine single bonds, this one you have sp2 hybridized carbon. This one has sp3 hybridized carbon. So this carbon chlorine bond is weaker than this carbon-chlorine bond. So the fact that this guy is more reactive suggests that this bond cleavage is involved in the rate limiting step. Basically, consistent with the first observation. Okay. So both observations suggest a carbon halogen bond cleave. Okay, is involved in the rate limiting step. Okay. So this suggests the mechanism. So you get a alkyl halide, okay? Then react with metal, and the metal will transfer a single electron to the alkyl halide, and that electron will be placed into the one of the lowest occupied antibonding orbital. That will give us a radical anion, and this step is not rate limiting. The first step is relatively fast. The second step is this radical anion will undergo rate limiting carbon halogen bond cleavage, give you an alkyl radical plus chloride ion. Then the methyl radical react with another metal lithium, give you the organo lithium compound. So this is the rate limiting step. Okay. Similar thing is happen between a halide, organic halide, and the magnesium. So the magnesium is going to transfer a single electron to the organohalide, give you radical anion. Then the radical anion will break the carbon halogen bond, and both electron goes to the chlorine, and then give you a chloride and a alkyl organoradical, and the organoradical combine with magnesium, single charge magnesium, and then give you the Grignard reagent. So the rate limiting step is the cleavage of carbon halogen bond of the radical anion. So let me just give you a quick exercise. So I'm giving you a few compounds. Okay. So 1, 2, 3, 4. Okay. Which halide is the most reactive in a reaction with metal lithium? Okay, very good. Okay, first one, because first it has a iodine, carbon iodine bond is weakest. Second, this carbon is sp3 hybridized. Okay, then which compound is least reactive when reacting with the lithium? Number 4, good. Okay, so the sequence will be, this is the most reactive. Okay, most, that's the least. Okay, and this will be second most reactive. Okay, this will be third most reactive. Okay. Basically, you have to look at the combination of halogen and the hybridization state of carbon. So why this one is the third most reactive? Because of this sp2 bromine bond is more reactive with sp2 chlorine bond, but obviously is less reactive than sp3 carbon bromine bond. And sp3 carbon bromine bond is not as reactive as sp3 iodine bond. Okay, so now let's look at the organolithium and organomagnesium compound property. Okay, first thing is, as I emphasized earlier, because of in carbon lithium and the carbon magnesium bond, the carbon is so much more electronegative than the metal. So we can essentially, it's not completely right, but it's relatively safe simplification. We can consider they are ionic and the carbon is negative charge. Okay, so so then if you consider organolithium, organomagnesium, or Grignard region, they are carbon anion, then you can immediately realize they are extraordinarily basic. If you refer the pKa table we learned in chapter 1 of organic 1. Okay, so the generally the carbon anions, conjugate acid, they are hydrocarbons. Okay, when we consider basicity of carbon anions, we need to look at acidity of their conjugate acid. They are hydrocarbons. Hydrocarbons generally have pKa somewhere between 25 and 70. Okay, and alkanes usually have pK around 60 something. So they are extremely basic. Okay, so for this reason, all those organometallic compounds can have no difficulty whatsoever completely remove the proton in the hydroxyl proton in the alcohol or the hydroxyl proton in water. So that's why if you want to do any reactions of Grignard or organolithium compound, you have to rigorously remove moisture out of solvent, out of the container, and avoid contact with moist air. Okay, because if you do that, the moisture, basically water, in the air gonna react with the carbon anion part of the either organolithium or Grignard and deactivate it, convert it into hydrocarbon, and then water itself become hydroxide ion. Okay. So that's why the solvent must be, you cannot using alcohol as a solvent, you cannot using water as a solvent, you cannot using carboxyl acid as a solvent, you cannot have thiol, those things all you cannot. So the only kind of most commonly used solvent either is just hydrocarbon itself or ether. And ether is more common use because it can help dissolve the metal part better. So now in some rare applications, we can make use of those extraordinary basicity of carbon anion, organolithium, or Grignard reagent to do some interesting the conversions. Like in this case, if we want to replace the bromine, okay, on this double bonded carbon with deuterium, we actually can first convert this vinyl bromide into a Grignard reagent. So the insert the magnesium into the carbon bromine bond. Then we know this guy is essentially carbon anion of this, okay, carbon anion of this the alkene, okay. Then you can add a D2O in it, and this strong base, okay, can deprotonate the the deuterium the DOD, install the deuterium at the site original bromine occupied. So that's one of applications. The second application is that because of the Grignard reagent or organolithium compound, they are the strongest base we have seen so far. So they often can be used to prepare slightly less basic organometallic compounds. For instance, if you have this ethyl magnesium bromide, you could react with acetylene because this alkyne proton is highly acidic among hydrocarbons. So this alkyne proton can be removed by the ethyl anion in the Grignard reagent. And that eventually give you the the Grignard reagent of the the alkyne, which is relatively difficult to directly prepare. Okay. And in organic chemistry, we often using N-butyl lithium or tertiary butyl lithium, for this kind of purpose, pretty often. Those are, you know, you can, those reagents you can buy from those chemical suppliers. They just use as extraordinary base to prepare, you know, the organometallic compounds of other type. N means the is normal, means the unbranched. All right, so the those are the just, you know, the for this, you know, basically the strong basicity, you know, the means that, you know, the that lead to some, you know, restriction of how to, you know, how should we use organometallic compound. So the solvent under the, you know, the under the, you know, in the reaction system, you need to avoid water, avoid alcohol, or avoid any compound can have relative, you know, the acidic, you know, the proton. If you want to keep the structure of the organometallic compound, you know, the for its intended purpose. Okay. So what is most like intended purpose of organometallic compound is actually, you know, the probably you can guess. Okay, because of this, you know, the organometallic compound can be, you know, organolithium and organomagnesium can be considered as essentially ionic. So the like organolithium can be considered of this plus this. Okay. So the lithium part, lithium cation part, is just spectator ions. Okay. So this part can make organometallic compound exceedingly basic, but also can make organometallic compound exceedingly what? Other than basicity, what else you can expect from carbon anion? Can anyone tell me? If we consider the anionic, okay, so the other than basicity, what else you can expect? Nucleophilicity, okay? Yes, very good, thank you. So the kind of reaction we mainly going to focusing on is the when the organolithium or Grignard reagent, okay, will be used as a, you know, the carbon-based nucleophile. Okay. So the kind of reaction we're gonna look at the most often. So basically, Grignard or organolithium, they are equivalent to carbon anion. Okay, as I said, it's a kind of a safe simplification. Okay, it's not exactly 100% accurate, but it's safe enough for us to, you know, the simplify our thoughts. Okay, so in addition of being a strong basis, okay, they also, you know, the make them excellent nucleophiles. Yes, basicity usually goes along the same direction as a nucleophilicity, but they are not exactly equal. Okay, but anyway, so being nucleophilic means they are potentially capable of reacting with the electrophile. So the kind of electrophile we're going to be dealing most often in this chapter is a carbonyl group. And let me emphasize, the carbonyl group is the most important group in entire organic too. And you know, the many aspects, you know, made the carbonyl group important. But the most, you know, I guess, you know, the two aspects you're going to see immediately is first, the carbonyl group is highly polarized. That, you know, four shared electrons highly polarized toward oxygen, because after all, oxygen is, you know, electron activity is 3.5, carbon is 2.5. So the two pairs of electrons highly polarized toward oxygen. That makes the carbonyl carbon highly electrophilic. So the carbonyl carbon can easily react with nucleophile. Second, because carbonyl group has a sigma bond and a pi bond. A pi bond is weaker than sigma bond, so the carbonyl group can undergo addition reaction. And mostly addition can happen, we're going to see is basically addition from the carbon anion in Grignard or organolithium add to the carbonyl carbon. So the general, the reaction mechanism shown here, we can assume this organolithium or Grignard just a carbon anion. So this pair of electrons will become bonding pair between the carbon and the carbonyl, okay? So once this R bound to this carbon, so we know carbon can have at least 4 bonds. So if this bonded, then this pi bond must move to the oxygen, and that gives us the intermediate, alkoxide intermediate. And usually that's the rate limiting step in the reaction between the organolithium or the Grignard with carbonyl compound. Okay, so this is the key reaction. Okay, so the rest of the magnesium thing or lithium, they're just counter ions. You don't need to worry about. Okay, so if you look at the reaction between the either Grignard organolithium with the carbonyl compound, the reaction typically is carried out in 2 steps. So in the first step is you mix organometallic compound and a carbonyl compound. The carbonyl compound could be aldehyde or a ketone. And so what is aldehyde? Is basically if you have a carbonyl, right? And at least one side is a hydrogen atom. Okay, the other side could be a hydrocarbon group or a hydrogen atom as well. Okay, so one side is hydrogen. Okay, so this side could be hydrocarbon or could be hydrogen. Okay, and then those both are considered aldehydes. Okay, and the ketones means that both sides of a carbonyl group you have a hydrocarbon group. Okay, so this is called ketone. So the actually it doesn't matter what kind of the carbonyl compound you have. Okay, the mechanism is exactly the same. So you always go like that. You don't need to really care about what are the groups on the carbonyl as long as they are either hydrogen or hydrocarbon group. So it always go like we don't care what here. Okay, we don't really care X, Y. Okay, so if you have an organometallic compound, just react with here. Assume X, Y, either they are hydrocarbon or hydrogen. Okay, X, Y, they are either hydrocarbon group, either hydrocarbon based group, carbon, or hydrogen. Okay, so that is in the THF, that's the first step. And then this gives you alkoxide ion. Then usually in the second step, you add an acid, okay? And then what happens, with acid, the acid just add a proton to the negative charged oxygen and give you the alcohol product, okay? So this is a general reaction of the, how the green organolithium or Grignard react with the carbonyl compound. Okay, so I'm gonna give you a number of examples. So I'm gonna give you a number of examples. Okay, so who has questions? No, THF is a solvent, not a catalyst. Okay, just a solvent. Okay, so let's give you example. Say first one. always two-step reaction. First one in THF or diester ether, that's a solvent, okay? Second one, say, add acid, okay? Now in the first step, mechanistically, you can consider this one is equal to methyl anion, okay, plus lithium cation, okay? This guy just spectator ion, don't need to worry about it. So the methyl anion is highly nucleophilic, attack the electrophilic, the carbonyl carbon, and that give you the, two hydrogen here, okay? Then in the separate step, in second step, you add a H3O plus. This must be written in two steps, okay? If you directly mix, all those things together, the reaction, the acid will kill organolithium compound, deactivated organolithium compound. So the net effect, when you have the methyl react with, methyl lithium react with formaldehyde, this is called formaldehyde, you are adding a CH2OH to the alkyl group. And look at another example. Then this time, let's say, using again, first step THF, second step acid, okay? So what happened in first step is the this guy, we know that we can consider is anion, vinyl anion plus magnesium Br plus. This is just a counter ion, okay? Forget about it. They don't really play active role in the reaction. So this anion attacks electrophilic carbonyl carbon. This are two lone pairs, and this immediately give you the this guy. You need to draw this kind of thing as I'm doing. Obviously, the hydrogen is still here. This finished what happened in the first step, okay? Then in second step, you add the proton. And the you get this alcohol. So what happens, the net effect is whatever carbonyl compound you have, okay, you're going to add the alkyl group, okay? So you get to add the organic group to the carbonyl carbon. And in the second step, the proton will be added to the carbonyl oxygen, okay? So net effect, you are adding, look, if you look at the reaction, you are adding a kind of hydrocarbon across the carbon-oxygen double bond, okay? The alkyl group, because nucleophilic, add to the carbonyl carbon because it's electrophilic, okay? And then the proton will be added to the carbonyl oxygen, and that protons come from the acid in the second step. We can look at another example. Where screen here, screen, okay. This time let's play a ketone. And say we are using a triple bond. again, but this one usually we do it in the the liquid ammonia, and the second one, if you want, we add acid. Okay. If you want using THF also is fine. Okay. But the liquid ammonia is more commonly used because if you recall, this guy can be prepared from alkyne from sodium amide in chapter 9 organic 1. Anyway, so in the first step and this guy again we can simplify it, consider it just carbon anion, okay, plus sodium cation, and this is spectator ions. You don't need to worry about it. So this is nucleophilic. We'll be attacking here, give you the alkoxide carbon anion. Okay, and then in the second step, the acid will be providing a proton to the alkoxide. Okay, so it will give you the final product. So again, you will see that you add a cross of hydrocarbon, add a molecule of hydrocarbon across the carbon oxygen double bond, and the hydrocarbon, because nucleophilic, add to the electrophilic carbonyl carbon, and the proton come from the acid, add to the come from here, okay, add to the carbonyl oxygen, give you alcohol. Okay. So this actually I use the example, the last example actually is the example of how do we using the organometallic compound of alkyne to make acetylenic alcohol, basic alcohol with carbon triple bond. So basically, just take the the carbonyl compound, okay, react with a conjugate base of terminal alkyne. So this one usually is prepared from the usually, if you recall what we learned in organic 1, usually prepared from this in ammonia, okay, usually, okay, and then react with the carbonyl. This guy is highly nucleophilic, as I showed you earlier, and give you alkoxide, then you proton it in separate step. So net reaction is you add a molecule of hydrocarbon across carbon oxygen double bond, and nucleophilic hydrocarbon part add to electrophilic carbonyl carbon, and the proton added to the carbonyl oxygen. So basically you see that we can use the reaction between a Grignard or organolithium and a carbonyl can be a very useful way for us to prepare alcohols. So it often is used in such a way. So let's say if you are asked to make an alcohol using a combination of organometallic compound, say organolithium or Grignard reagent with a carbonyl compound. So how should you do that? Okay. So generally, we can, if we have that such a nucleophilic, this kind of nucleophilic addition in mind, okay, you can consider, in the alcohol, in the alcohol, there's 3 groups connect to the, the carbon next to the hydroxy group, because we know, typically this carbon is sp3 hybridized. One of them connect to hydroxy group. There's 3 other group must bond to this carbon. So you can consider one of them is come from organometallic compound, and two of them come from the carbonyl compound. So if you have the secondary or tertiary alcohol, so there's multiple way of disconnecting molecules can be made. Okay, for instance, if you want to make this compound, right? We can consider this thing is from Grignard reagent, and those two guys, okay, are from the carbonyl compound. So this could be a way of making the alcohol. But we also can consider this guy, okay, is come from organometallic compound. Those two groups come from the carbonyl compound. That means we are using this combination. Yes, still work. Even you could consider, this guy, okay, come from organometallic compound, and the other two from carbonyl compound, and this also works. So it often basically, all these things, if you have tertiary alcohol, you have three possible ways. All of them may work. But if it's primary alcohol, you only have one way, because you cannot using, the hydride, okay, as organometallic compound.